Hi folks, it is our pleasure today to have with us Professor Jennifer Rexford from the Computer Science Department at Princeton University. She basically worked at AT&T for several years where she designed quite a few of their network management tools. She's been very active on the network system side in particular and was the chair of ACM SIGCOMM for many years. She is an ACM Fellow as well as has received an ACM Award for Outstanding Young Computer Professional in the year 2005. And she's been very active on the open flow side of things more recently, and I think that's what she's going to talk about. So please welcome Professor Jennifer Rexford.
Great, thank you. It's a pleasure to be here, even if virtually. So the Internet's really a remarkable story. It's a research experiment that escaped from the lab to become essentially a global communications infrastructure. And part of the reason for that, I think, is relevant to the discussion about software-defined networking, which is what I'm going to talk about today. And I think one of the reasons the Internet's been so successful was not so much in what the early designers of the network chose to put in to the design of the Internet, but what they chose not to put in. And so by choosing to underspecify the design, by having a very simple best effort packet delivery model, and to have programmable functionality on the end hosts, allowed a lot of innovation and lowered the barrier for a lot of people to contribute to that innovation to make the Internet become something much more than the early designers of the Internet could ever really foreseen in advance. But ironically, that kind of innovation is primarily only possible at the edge of the network and not on the inside. And so the inside of the network is actually a completely different story. We have closed equipment where the software associated with routers and switches is bundled with the underlying hardware, and the interfaces to those boxes are vendor specific and often fairly baroque. The protocols are highly specified. The process of changing a protocol is a multi-year standardization activity, and very few people in the end are able to innovate. Really, it's primarily the equipment vendors who write the software and determine what the configuration interfaces are. And even for people who buy that equipment, there are very long delays for introducing new features into their network because they have to work indirectly through their equipment vendors or through large standards bodies to affect change. So one might argue, well, do we really need innovation inside the network if the inside of the network is so simple? But in practice, the network has become incredibly complicated with new point solutions every time a new need arises. And so we have routers, switches, firewalls, network address translators, load balancers, access points, and so on, a huge proliferation of lots of different kinds of boxes and lots of different kinds of interfaces, with network administrators forced to hold it all together with duct tape, essentially managing each of these boxes individually without having very good network-wide visibility or network-wide control. And so that's the state of the situation now, where the cost of running a network overwhelms the cost of even buying the equipment because of all this complexity. And the people who are dealing with this complexity don't have much of an ability to fundamentally change the way their equipment operates. So software-defined networking is an attempt to enable a larger set of people to innovate inside the network. And it does so by separating the control and the data plane from one another. So the data plane is all the packet processing that forwards or floods or drops the packets as they flow through the network. And the control plane is the distributed algorithms that today run directly on top of the network elements, standardized inside the IETF so they can interoperate from one box to another, and implemented in proprietary code. But in software-defined networking, these two are separated by having an open interface between the control and the data planes. So that control plane software written by other parties can install packet processing rules in the underlying switches. That's sort of the first main idea in software-defined networking. And the API that's very popular today, although it's certainly not the only way you could do this, is OpenFlow, which was developed by Nick McEwen's group at Stanford. And so an OpenFlow is a very simple model of the packet processing capabilities in the switch. Essentially, the switch has a prioritized list of rules that have, each rule has a pattern that dictates which packets match the rule, and that can match or wildcard on different bits in the packet header, like the IP addresses, the MAC addresses, the TCP, UDP port numbers, and so on. There are a bunch of actions that can be performed on matching packets, like dropping them or forwarding them out a particular output port or sending them to some other software for more processing. There's a priority to disambiguate between rules that overlap with one another, and finally some counters that indicate how many packets and how many bytes have matched these rules. So I just show a simple example here with 3 different rules that overlap in part with one another. And as you can see, what's nice about this is you can actually have the semantics of a firewall, a router, a switch, a whole bunch of different kind of boxes I had on the previous slide, just by what rules you choose to put in the switch. If the rules primarily drop or forward packets based on a whole bunch of header fields, we have a firewall. If it forwards based on the destination IP address, we have an IP router. If it's forwarding based on MAC addresses, we have a switch. If it's rewriting the IP addresses and port numbers, it may be a network address translator or some odd combination of all of these. So in some ways now, we can implement a whole bunch of different kinds of network functionality just by deciding what kind of rules we want to dynamically install in these underlying switches. And the other thing that's nice is this functionality is pretty similar to what existing device hardware already does. And so a lot of vendors support OpenFlow, HP, NEC, Quanta, Dell, IBM, Cisco, Juniper, and so on, all have equipment that support the OpenFlow API because it was not really a matter of spinning new hardware. This was really a matter of having a standard interface to what is already available in the hardware of a lot of existing commercial switch implementations. So that's OpenFlow. Now, there are newer versions of OpenFlow that are more sophisticated than what I described here, but this is sort of I think, a good level at which to understand it. The newer versions of OpenFlow have multiple stages of tables that can match on different subsets of fields in the packet and do different subsets of actions. But this implementation I described here is something that's quite amenable to being implemented with a ternary content addressable memory or TCAM. And that's a very common way to implement an OpenFlow switch in hardware. So that's OpenFlow. The other main idea in SDN is rather than having the control software that installs those rules be located on every single network element, the idea is to move that to one or a small number of controllers that are separate from the data plane elements. And so what that means is that now applications, rather than distributed protocols, can run on top of the controller platform and dictate, based on a network-wide view, how the network switches should perform. And so essentially now we have direct control through the OpenFlow API, and network-wide visibility and network-wide control through the controller platform, moving away from having distributed protocols to having applications that run on top of the controller platform. So those are the two main ideas, an open data plane API and a logically centralized controller. So just to give a couple examples, and by the way, if people have any questions, feel free to interrupt me at any time. It's a little hard for me to gauge if people have questions or not, so feel free to just wave. I just want to give you a couple examples of really simple SDN applications to both show the flexibility of SDN and also to illustrate a little bit more of how it works. So imagine we've got two hosts that are communicating with one another. The rules installed in the network that are forwarding the packets from each of these devices to the other. And now one of the devices is going to move. Now, how are we going to get the traffic to follow this device to its new location? Well, one way to do that would be, by default, to have rules in the switches that forward traffic from unfamiliar source addresses to the controller. And so when this iPhone sends a packet, it never had sent a packet at this location before, and so that packet will be sent to the controller. It'll match a rule that says, hey, for these kind of packets, the action is forward to the controller. And when the controller gets that message, it realizes that this particular input port is now associated with the new source address, a source IP address or a source MAC address. And based on that, an event handler can get invoked on the controller that will cause it to install new rules in the switches and remove old rules that will now allow these two hosts to communicate over a different path through a different set of rules and a different set of switches. So the two hosts now are communicating using the same addresses over new paths unbeknownst to them. And that's one simple example. Now that was an example of a reactive application where a packet had to go to the controller to trigger the behavior of updating the rules. As you can imagine, in a large network, that might not be quite practical because it's going to put a lot of burden on the controller. We want to keep as much traffic in the data plane on these fast but dumb switches as possible. A second example is server load balancing, which is a really common application in data center networks. So here we want to split traffic coming from different users over multiple copies of the same website. Now today, people would buy a dedicated appliance for this purpose and install it on their network. But you can do a simple form of server load balancing just by installing the appropriate rules on the switches. And so here I show traffic destined to a single public IP address, 1.2.3.4, being split based on the IP address of the sender. For half of the clients whose addresses start with 0 are going to one copy, and the other half that start with 1 are going to the other, simply by having sets of rules installed in the switches that match on the appropriate source destination patterns and maybe rewrite the destination address to match that of the appropriate backend server and the traffic following paths using that new address to go to the right server replica. And so by pre-installing in advance these two rules in each of the switches, we now have a load balancer without any traffic having to go to the controller. Now, these are just two examples. In fact, what's interesting is these are just two of many examples. And so here's just a list of a bunch of applications people have been developing on top of OpenFlow using the same basic approach: seamless mobility and VM migration, server load balancing, dynamic access control policies, being able to spread traffic over multiple access points in the network at the same time, selectively shutting down parts of the network to save energy during periods of low load, adaptively changing the rules on the network to monitor different subsets of traffic, using that to detect denial of service attacks and block it, or even virtualizing the network by allowing different controller applications to manage different subsets of the traffic. And if you go to the openflow.org website, there's actually a number of nice videos giving demos of a bunch of these different applications. I should say this last one, network virtualization, is one that has seen quite a bit of startup activity, and I'll come back to that point later. That's been a very popular application in data center networks. So don't just take my word for it. Actually, this has become a really major trend just in the past few years. The Open Networking Foundation has dozens of companies that have come together to focus on standardizing OpenFlow and other SDN technology. And I just show here the companies that are on the board of directors. Some of these won't surprise you. We see a lot of cloud and data center based companies, but you also see some carriers like Deutsche Telekom and Verizon, and you also see Goldman Sachs. So financial services firms are also, I think, doing a lot of IT spend, and they're also getting interested in SDN as a way to be able to more flexibly manage the network at lower cost. Last year, in April, Google announced publicly that they're running software-defined networking on their global private backbone network that interconnects all their data centers. It's estimated that 10% of the traffic on the internet runs over this network. So it's a pretty major OpenFlow deployment that they built using their own switches and their own controller software. And finally, the first startup company in this space, Nicira, which is a network virtualization solution built on top of OpenFlow, was bought by VMware last year for $1.26 billion. So as you can imagine, that's definitely increased the amount of interest a lot of people have in this topic. So these are just a few different examples. Are there any questions about SDN itself before I go on?
I think we're good, thanks.
Okay, great. So what I want to talk about really in this talk is software-defined networking has made it possible to program the network, but it hasn't really made it easy. And that's where our project comes in, which is called Frenetic. It's a joint project between Princeton and Cornell, and between programming languages researchers and networking and distributed systems researchers like myself. So our goal is to figure out if programming the network is such a good idea, what's the right language or the right abstractions to be able to make it possible to build sophisticated applications on the controller. So I want to talk a little bit about why programming SDNs is hard. So the good news first, I've already said these things, but just to reiterate them, SDN is good because it offers network-wide visibility, whereas today we have sort of box-level visibility. It offers direct control over the data plane and the switches rather than the indirect control today's distributed control planes offer, and it has a very simple, appealing, kind of Boolean logic-based data plane abstraction. All of that's good. The bad stuff is that the interface to programming the network is the same as the interface to the switches themselves, the OpenFlow API. And if that means that the functionality of applications that run on today's controller platforms is tied directly to the underlying switch hardware. It's a little bit like writing an assembly language. And in addition, these applications that run on the controller have to manage the priorities of rules they install, how many rules are available in the switch, and fairly low-level bit twiddling. Similar to doing register allocation by yourself rather than having a compiler do it. And then finally, it gets a little worse than that, because in practice, you often want to do multiple things in your network at once, load balancing and mobility and routing and monitoring and firewalling. And right now, there's not very good ways to be able to build one application that encompasses all that functionality without that application turning into a very large monolithic program that's very hard to write, test, and debug. And so that's the issue we're trying to address, is to be able to create abstractions that will allow programmers to build modular applications and not have to deal with these very low-level resource allocation questions in dealing with the underlying network. So we divide our thinking about this into three parts, kind of matching the control loop of managing a network. So if you manage a network, you're monitoring the network to know what's going on, detecting congestion or attacks. You're updating your policy for how you want to manage the network. And then you're finally affecting a change in that policy by actually reconfiguring the underlying network elements. And so we have abstractions I'm going to describe in this talk for each of those three pieces. So essentially what we have in Frenetic, sorry, my slides are not moving. Let's try that again, is a language for querying network state, an ability to build applications out of multiple independent modules that implement different parts of the control logic, and an update abstraction that allows the network operator or the person writing the control software to update the network as if it was updated instantaneously, even though in practice there's a distributed collection of switches that are updated at different times. And so I'm going to go in each of those three parts in that order, but I'm going to put the most emphasis on the middle part on module composition. So first I'm going to talk about monitoring, reading network state. And I'm going to just go through a few different abstractions we've introduced here. So monitoring in OpenFlow really is two different pieces to it. One is that each of the rules installed in the switches have counters associated with them. They count the bytes and the packets. And the second is that some traffic or some events can go to the controller to influence the handling of future traffic. So first, just focusing on the traffic counters. It's all well and good to have these traffic counters, but often what you want to monitor is more complicated than can be expressed in a single rule. So just take a simple question a network administrator might have. How much web server traffic do I have in my network that does not come from source 1.2.3.4? You'd have to have more than one rule to implement that negation of the except for source 1, 2, 3, 4. And so there's two rules I show here. The first rule, the higher priority one, matches the web traffic that is coming from this source. So that traffic will match the first rule, and all other web traffic will fall through to the second rule of lower priority that matches only on the fact that it's TCP port 80 or web traffic. And the counters in that second rule will allow us to answer the query that the user is interested in. So this is pretty complicated, and even in this simple example, you're having to think of multiple rules and how they overlap with one another. So a very simple thing we've done, it's not rocket science, but it's useful, is to allow the programmer to operate in predicates rather than in individual OpenFlow rules. And our underlying runtime system will translate a predicate like the one I show here, source IP address not equal to 1.2.3.4 and source port is equal to 80, will translate that into a prioritized list of rules that implement those semantics. Second thing, perhaps a little bit more interesting, is that the number of rules that are available in the switch is limited, and it's something we'd like to shield from the programmer. So imagine that the programmer wants to be able to compute a histogram of traffic by source IP address. There are a whole bunch of 2 to the 32 different source IP addresses, so installing rules for all of them in advance would not be feasible. So instead, what a programmer would do if they wanted to solve this today is they would have the first packet from any new source IP address go to the controller, realize that there's a new source IP address, and install a rule to automatically monitor the remaining traffic that comes from that source IP address. So kind of tedious. This is something we provide automatically by what we call dynamic unfolding. So the programmer can basically say, I want to collect some statistic grouped by some set of header fields, in this case source IP address, and we'll automatically dynamically install the rules as traffic arrives into the network to install one rule for each instance of that pattern, or one set of rules for each instance of that pattern, and periodically query the counters to return a stream of those statistics to the programmer.
Quick question.
Case, for example, yeah.
On the previous slide, you were indicating priority on the rule that gets compiled out from the predicate. How do you actually handle the precedence? Is the precedence just based on short-circuiting of that expression itself? Or is it based on... Go ahead.
So the way the OpenFlow switch works is you get to install the rules with the priority that you dictate. And so we'll translate this predicate into the negation happening first, and the absence of negation following through. So we essentially have a little compiler that will turn these Boolean predicates into the right priorities.
So it's just based on lexicographical order of the subterms?
So if there's an and operator, if there's a negation, we need to have something that matches on the truth and fall through to the absence of it. If things are just anded together without negation, we can often put those together just in a single rule. So for example, if the query were source IP address equals 1234 and source port equals 80, that could become one rule that just matches on all those fields. Ors become a sequence of sets of rules because we need to be able to do one thing and we do it for the next set of predicate, the next term in the predicate, and so on. So essentially negation turns into matching on the negative, falling through to the positive, and turns into one rule, and or turns into a set of rules that match on each of the terms in the or clause.
Okay.
Does that make sense?
Yep.
Cool. Cool. So the third thing I wanted to mention is a common programming idiom in OpenFlow is that the first packet of a group of packets goes to the controller. This is what happens if you don't know ahead of time how you want to handle a particular kind of traffic, or you just don't want to use the space in the switches to install rules ahead of time. You might send the first packet of a large traffic aggregate to the controller, and then the controller will install rules that will handle the subsequent packets that look like this one. In the simplest case, you might imagine the first packet when a host moves to a new location, like the mobility example I mentioned earlier satisfies this. So in the simplest case, the packet goes to the controller, and then the controller, based on whatever the programmer has said to do, will install rules. Now, unfortunately, this doesn't happen instantaneously. And so the difficulty here is while the controller is installing the rules, a second packet that matches this pattern may also arrive and also be sent to the controller because there are no rules yet in the switch to say to do otherwise. This forces the programmer to deal with a lot of complexity. They now have to think about how to make sure to handle that second packet in a way that's consistent with the first one. Even though they've already decided how to handle the first one, they just have to worry about the fact that the rules might not have yet reached the switch. And this can lead to a lot of problems. So what we do is we actually hide this from the programmer. If the programmer only wants to see the first packet, we allow them to say that, or if they only want to see the first K packets, we'll let them say how many they want to see. And if extra packets come to the controller, because race conditions like this can certainly happen, the controller already knows how the programmer wants these packets to be handled and can hide the actual handling of those packets from the programmer and just handle them directly at the controller. Now, this particular kind of problem I mentioned actually has caused a lot of bugs in early OpenFlow applications where programmers fire and forget. They handle the first packet under the implicit assumption that the second packet will never get to the switch before the rules get installed. In fact, in a different project of mine, we did some work on model checking of existing OpenFlow applications, and we found this bug in a significant fraction of the OpenFlow applications that we tested. Because it's very easy to overlook the fact that under corner cases, extra traffic might in fact arrive at the switch before the rules are actually successfully installed by the controller. So here we just let the programmer say exactly what he wants to see, nothing more, nothing less. And so that's the basic abstraction that we provide, and we embed this in an SQL-like language that's sort of familiar to many programmers, where you say exactly what you want to see, nothing more, nothing less. And then the runtime system underneath will install rules as necessary to make the right packets go to the controller or to query the right counters and make sure that the programmer doesn't have to deal with all of this sort of interaction with between the controller and the switch to make this happen. So just to show two examples, one that does traffic monitoring. Imagine I want to do a histogram of traffic coming in from the internet, let's say on input port 2, that's TCP web server traffic on port 80. And I want to histogram that by what destination MAC address on my network that traffic's going to. Then I would say I want to see the bytes, where they're coming in from a particular input port and matching a particular TCP port, grouped by MAC address, and I want to see it every 60 seconds. That 4-line query will turn into one or more OpenFlow rules to represent the predicate, dynamically unfolded every time there's a new MAC address, and automatically pulled every 60 seconds, returning simply a stream of pairings of MAC addresses with the amount of traffic they have every 60 seconds. Second example that corresponds to the mobility example I presented earlier, an application that wants to learn the location of mobile hosts as they move now wants to actually see a packet from each of those mobile devices each time they move so that they can track the location. So here we want to see the packets, not just the count of the number of bytes. And we want them grouped by source MAC address so we know when the source has moved to a new location. Split by input port. In other words, every time it switches to a new input port, we want to know about it. But we only want to see the first packet that that host sends at that new input port. And again, this 4 lines of code will send a single packet up to the controller application every time a source address appears at a new input port, allowing mobility to be tracked. Now, not only can the programmer write either of these queries, they can write both of them, and we'll take care of, under the hood, of doing the necessary composition so that what the programmer needs to see comes up to the controller to be able to do both the traffic monitoring and the monitoring of host location. So you can still do a histogram of traffic by destination MAC address while you're simultaneously learning where the locations are of all the source MAC addresses. So that's that first part of frenetic is this query language. It lets the programmer now operate at a higher level of abstraction for understanding what's going on in the network. The next piece of frenetic, which is probably the meatiest part of the talk, is how do we take information we've gleaned from the network and decide how to change the way the network behaves. And in particular, the question we're interested in here is how do we build something other than a monolithic application. If we want to support monitoring, routing, firewalling, load balancing, and a whole bunch of other things, we don't want to build one really monolithic application that we would have a difficult time testing, debugging, and reusing. Instead, we'd really like to be able to let there be a module for each task, written independently, and combined together to build one more sophisticated application. This is just motherhood and apple pie. We'd like to do modular programming. The reason this is hard is these applications our application modules are handling the same traffic, but they're not completely separate applications. I don't want to monitor some traffic and route other traffic. I want to monitor and route the traffic and have traffic be subject to a firewall policy and traffic that's going to a replicated web server be load balanced. So the real challenge here is how do I actually modularize when I actually want each of these modules to affect the handling of the same traffic. So there has been work on a simple version of this, which is that startup company Nicira that I mentioned earlier does exactly what I'm about to describe here, which is they want to support in the data center multiple tenants, each of which have their own subset of traffic running over the network. In other words, they'd like to slice the network and give each tenant or each customer their own slice of the network. In this case, there are multiple application modules running on the controller, each operating on behalf of a different subset, non-overlapping with the others of the traffic. So this problem is an incredibly important special case, but for us it really is a special case because each of these modules handles a different subset of traffic. They don't have to coordinate in any way. The main objective here is isolation. We want to make sure that each slice's module only sees the traffic it's entitled to see and only installs rules that affects its own traffic. And likewise, if there's bandwidth resources or rule space in the switches, we'd also like to partition that so that we can minimize the interference in terms of performance that each of these different modules would see. But our goal really, more generally, is to allow each of these modules to partially specify the functionality of handling the same traffic and coordinate how those should work together in a single application. So that's our challenge. So I want to go through a couple examples of ways we do that. So one thing we do is support what's called parallel composition. So parallel composition is essentially saying that if I have two different modules, I want the illusion that if they both operate in parallel on separate copies of the same packet. Even though in practice, inside the network, I may not actually duplicate the packet. So really simple example, imagine I've got one module that's trying to monitor traffic, compute a histogram, for example, by a source IP address, and another that wants to route traffic based on the destination address. I'd like to do both. I'd like to monitor the traffic and route it. So the monitoring application might generate policies that, let's say in this case, match on this one source IP address, and the action they want to perform on that traffic is count. And the module that's doing routing might generate rules of the type where they're matching on the destination IP address, and the action is to forward out a particular output port on the switch. Now, if we wanted to do both of these things at the same time, the way this would actually have to look under the hood is what I show below, which is a prioritized list of rules that are going to both monitor and forward. And essentially what's happening here is what's happening under the hood is a cross product, where any traffic that has a particular source IP address will be counted, any packet with a particular destination IP address will be forwarded, and essentially you end up with this mix of rules that if the programmer were writing his own code monolithically, the programmer would have to generate the spaghetti at the bottom. Our goal is essentially to allow the programmer to just write each of these two modules independently and just say, do both, and have their underlying runtime system take care of generating the appropriate prioritized list of rules that does the semantics of both operations in parallel. So that's parallel composition. Now, as you can imagine, parallel composition is a reasonable abstraction when one of the modules is doing some sort of action like forwarding the traffic, and the other is just passively monitoring. But it doesn't make sense to do parallel composition if you're trying to do multiple parties are trying to write or forward the same traffic. And so sequential composition is the other simple operator we offer. And so the load balancing application I mentioned earlier is a great example of sequential composition, where I might have a load balancer that wants to split traffic going to a particular destination. Let's say based on the source IP address. Well, half the traffic is going to go to one replica of the server with destination 10.0.0.1, and the other half is going to go to 10.0.0.2. So the load balancer essentially takes an action on the traffic to rewrite the destination address, but not to make any forwarding decisions about how to reach that destination. And the routing module, not knowing that there's any load balancing going on at all, is purely going to dictate how do I reach those destination addresses of these servers. So again, these two modules can be written independently of one another and each generate a set of rules in the network that will implement their particular part. The programmer can then say, I want load balancing to be done before routing, in sequential composition with routing. And so I showed this sort of like piping load balancing into routing. And under the hood, the runtime system can take care of implementing a set of rules that do both, one followed by the other. So here, for example, if you look at the first rule at the bottom, I have the pattern that existed in the first rule in red. I'm going to rewrite the destination address and forward the traffic as if the destination address had already been rewritten. And so one rule will essentially do the semantics of following the packet through two switches, essentially one that does the policies of load balancing and one that does the policy of routing, but in practice is implemented on a single switch that does semantically one followed by the other. So together, parallel and sequential composition give us a really powerful way to take multiple control modules that each operate independently and allow them to work in concert to handle the same traffic. A small generalization of that is just to add predicates that dictate which traffic go into which combination of modules. So here, for example, I might say only the web traffic goes to the load balancer, followed by routing. And maybe the non-web traffic I go to a monitor in parallel with routing. And so I can essentially snap together lots of different modules with different subsets of traffic going through different combinations of these modules to implement the more sophisticated application. So note here that the programmer is really doing two things, writing these individual modules and also deciding how to combine them together and which traffic should go through them. In practice, you might imagine different programmers doing these two tasks. So the load balancer might be written by a third party, the routing might be managed by another third party, the network operator might be the person that decides that load balancing is done.
So Jennifer, a quick question. Okay, so you have now effectively multiple traffic rules you're specifying, and you're back into this firewall problem, right? So we have a packet coming in, it could match against multiple rules. How do we decide what is the right action that's going to take place? How do you solve that here? Again, are we resolving the problem, or?
So the way that gets solved here is the programmer is dictating whether the right semantics is that both policies get done on the same packet, like the monitoring is done as well as routing, or that load balancing is done ahead of routing. So it's really as if the packet goes through the load balancer first and then routing. So there's sort of precedence, if you will. Like imagine you have a firewall and then you want to route only the traffic the firewall chooses not to drop. Then you'd have firewall sequentially composed with routing. So only the packets that don't get dropped by the firewall policy are forwarded based on whatever the routing policy is. So that's the programmer.
I'm talking about the example you're showing here. You're saying web traffic with destination port 80 going through a load balancer and routing, non-destination port 80 doing something else. Those two rules. They look like the firewall, same issue as the firewall issue now, right? And let's say if I
Yeah, you're totally right, and I think that there's no free lunch here. The programmer has to decide what precedence there is and whether it's possible. If more than, for example, here I show two non-overlapping things, web and non-web. If the programmer had overlapping predicates here, we'd have essentially the semantics of two copies of the packet going through the network, which is essentially what parallel composition does. So we don't do any magic under the hood here. If there's inherent precedence that needs to be obeyed, the programmer essentially enforces that by what predicates he puts on which traffic goes into which modules and what ordering, if any, you put in composing them.
Okay.
So that's all well and good, but it's not quite enough. I mean, we don't necessarily want, let's say, a load balancing module to be able to influence the handling of traffic at every hop through the network. We wanted, in the example I showed in the previous slide, to just rewrite the destination address, to pick the server replica but not do routing. So we need a way, beyond what I've described so far, to provide information hiding and protection, to limit what a module can see and to limit what a module can do. And what a kind of appealing abstraction we provide here is to give to each module the abstraction of a network topology. This network topology could be the real topology. In the case of a routing module, like on the right here, we would show the real topology because you want the routing module to compute paths through the network and decide what rules should go in the switches to affect that policy. But if you're doing a load balancer, you might want to have the illusion that the load balancer is just a single box, much like today's appliances are. And so we can present, the program can present to each module an artificially constructed topology that maps to the physical one. So for example, the load balancer might think the network is one big switch, and all it does when traffic enters that one big switch is just rewrite the destination address to that of the chosen server replica. The implementation of how to reach that server replica in practice might be done by the routing module. So by presenting this abstract topology, we're both hiding information the module doesn't need to see and also limiting what it's able to do. It's not able to influence how forwarding is done because it doesn't even have an ability to see, let alone install policy on the underlying switches that implement the routing. And the good thing is, from the programmer's point of view, this is no different than if the network really was actually a single one big switch. It doesn't really know the difference. It's still seeing a network. It's just seeing an artificially constructed one that hides a lot of detail. So we can essentially build a load balancer on this simple central one big switch abstraction and have it work in a distributed fashion over a collection of switches by having the runtime system actually install the rules that map this underlying, map to the underlying distributed collection of switches. And if the routing changes, like I show two different paths here on the right, if a link fails or due to network congestion, the routing has to change. That doesn't trigger any events that are seen by the load balancing module because it doesn't affect the virtual topology or the abstract topology that that load balancer sees. So it shields that module from having to see that detail. So that's the second piece, so that each module now can be composed in sequence or in parallel with other modules. And each module is actually operating on its own network object, if you will, that is its own view of an underlying network. Under the hood, the runtime system is going to have to map the virtual network down to the physical and to compose things sequentially and in parallel as defined by the programmer. That's the second piece. So I want to give an example of how this can work beyond the ones I've given so far. Imagine you want to implement an enterprise network. So a lot of enterprise networks are sort of an Ethernet island or a collection of Ethernet islands connected to an IP core. So you're running Ethernet protocols on the left, shortest path IP routing protocols on the right, and have a gateway switch in the middle. Now in practice, a gateway switch today is a complicated beast. It's speaking Ethernet out one side of its mouth, IP out the other side of its mouth. It's supporting ARP to be able to handle address resolution and so on. If we were to implement this in an OpenFlow application without Frenetic, this would be one big monolithic application where you chose which functionality to implement depending on whether events were happening in a blue switch, a green switch, or this hybrid switch in the middle. Now, in Frenetic, the way we can implement this is actually by three different modules. One that's an Ethernet module that operates on an abstract topology that includes only the 4 switches on the left. Another module that does shortest path routing based on IP addresses that operates only on the 4 switches on the right. And a simple little repeater that does ARP that operates on this purple switch in the middle. Now, in practice, the 3 switches that I show in the middle here in the red box are actually virtual switches that all map to the same physical switch. So in practice, the 3 hops that go through these 3 switches will be implemented by one set of rules under the hood, but the programmer doesn't have to deal with that. The programmer that writes how to do Ethernet learning doesn't have to treat that gateway switch as special. It's just one of the 4 switches that are in that network, and likewise for the green switch on the right. So in the first example I had a few slides ago, one big switch for a load balancer is actually implemented in a distributed collection of switches underneath. Here's the opposite. I actually have multiple virtual switches that combine together to form a single physical switch. So the topology abstraction can kind of go in both directions, many to one and one to many, to allow, again, modular applications that can gateway between different kinds of applications that might run in different parts of the network without treating that gateway as something special. So at a high level then what we've got is a bunch of application modules that might be written by third parties, and then a main program that dictates the virtual to physical mappings that each of these modules should see, and what kind of composition should be done to combine the modules together into one main program. And then the key here is that the secret sauce is in the controller platform underneath, we're mapping events that happen in the physical network up to their appropriate manifestations in all the virtual networks. And likewise, when rules get installed, we're taking care of composing them together to generate synthesized rules and mapping those rules down to the physical switches underneath that those virtual topologies map to. And all that kind of technical bookkeeping is being done in the runtime system itself. Okay, so that's the second part of Frenetic. The third part I'm just going to touch on really briefly relates to actually installing those rules in the underlying switches. And this is some work on what we call consistent updates. So in practice, whenever you want to update the network with a new set of rules, you often have a problem that you can't really update all the switches instantaneously. And so when you're switching the network from one policy, say the purple policy, which is one set of rules on the switches, to the green policy, which is a new set of rules on the switches, you may be worried that in packets in flight during this transition may not really obey either of the 2 policies. They might go through a purple switch followed by a green one because one switch was updated before the packet reached it and another was updated after. And so what you might have in the transition, as we see today on the internet, are lots of transient violations of things like not having loops in the network or having packets get dropped or having security policies violated because the network is in a temporarily inconsistent state. So we'd like to give the programmer an abstraction that they can imagine they update the network in one fell swoop. To give a second example of how this can happen, and we've seen this bug in a lot of OpenFlow applications, again, there's this model where often the first packet of a group of packets goes to the controller, and the controller installs a collection of rules in the switches, let's say to put a new path in place for this packet and other packets like it. If the controller successfully installs a rule in the first switch, but the second and third switch have not yet successfully installed those rules because it takes time. The packet in flight may reach the second switch before the rule that needs to be there to handle it has been successfully installed. This packet may now be either sent to the controller or, worse yet, match a rule that actually it could never have matched, a lower priority rule that's already in the switch, and be handled differently than the programmer intended. So in this project I mentioned earlier where we did model checking of existing OpenFlow applications, we found this bug a lot too. It's very easy to assume the rules are installed instantaneously or installed in the order that the programmer specifies. But in practice, each of the switches takes time to receive the message from the controller and commit. So as a result, you can have rules installed in a different order than the programmer intended. And have, now even checking for these bugs is expensive because the checker also has to worry about all the different orderings and timings of packets and of installation events in the network. So it's actually quite painful even to try to detect these kinds of bugs. And it's certainly easy to make these kind of bugs, and they're actually hard to catch. So we'd like to, again, find a way for both the programmer and any verification tools that are going to be used by the programmer to not have to deal with this combinatorial explosion in the number of packet and event orderings that can happen. So essentially what we want is a notion of consistency. And we call one notion of consistency we have is we call per packet consistency, which is that every packet is processed either in its entirety throughout its journey in the network by policy P1, the old policy, or through every hop in its journey by policy P2, not by any mixture of the two. And this is useful for guaranteeing things like access control policies are obeyed, that paths don't have loops or black holes. Now, that's not enough, unfortunately, for a lot of applications. Some applications need a richer notion of consistency we call per flow consistency, where a group of related packets, like all the packets in a single web download, are handled by the same policy. This is useful for load balancers, where you don't want part of your connection to a web server to go to one copy of that website and the rest of the packets to go to another. So here we want all packets in a group to follow either policy P1 in its entirety or policy P2 in its entirety, but never a mix of the two. That's obviously a stricter requirement than the first one, because now we have a property that has to hold across a collection of packets over time rather than just a single packet. So how do we do that? So we have an algorithm for doing this. So similar to a two-phase commit. Essentially what we need to do is we need to install the new policy in the network, but we don't want any packets to start using it until we've actually successfully installed it everywhere. So one thing we can do, because OpenFlow gives us a lot of flexibility, we can actually stamp packets when they enter the network with a version number using, let's say, a virtual local area network VLAN tag. So the rules that are installed at the network when you install P1 or P2 tag the packets at the ingress of the network with the version number associated with that policy. Now when it's time to install a new policy like P2, we first do a set of what we call unobservable updates. We update the interior switches to match on the new VLAN tag number 2, but no packets are yet entering the network that are being tagged with 2. And so there's no risk that these rules will actually match any packets yet. Once all the interior switches have successfully told the controller that they've installed the rules, we do a collection of one-touch updates asynchronously around the perimeter of the network, switching the tagging of packets to tag with P2. Each packet enters the network only once, and so once it enters the network, it's either tagged with the old tag and follows the old policy through the network all the way through, or it's tagged with the new policy and follows the new policy all the way through. After all the edge switches the controller that they've successfully started tagging packets with P2, we can wait for the amount of time that it takes packets to traverse the network, typically just a few tens of milliseconds, and then remove all the rules for the old policy because no packets are still in the network that are stamped with that version number. So this two-phase update will essentially ensure that packets in flight obey either P1 or P2, but never a mixture of the two. So we can do some optimizations. One optimization we do, as you can imagine, this two-phase update is pretty expensive, and because it can actually double the number of rules in the network. And that's clearly expensive, especially when the switch tables are implemented using high-speed memory like TCAMs that are quite power-hungry. In practice, we can often limit the scope of an update to a subgraph of the network if only part of the network is changing, or to a sub-portion of the traffic. Maybe only the web traffic's rules are changing, and we don't have to do a two-phase update for the parts of header space that are not changing. And there are also a number of special cases like adding a path for new traffic or removing a path for old traffic that can be done more easily because we're only affecting a chain of switches in the network rather than a whole graph. And so what our runtime system does is when a new policy is installed by the application, we do a diff of the old and the new policy and figure out which of these optimizations we can successfully apply and then do the appropriate update to the network. Another thing that's really interesting here is that when the programmer tells us P1 and P2, the only thing he has to tell us is that he wants either a per packet consistent update or a per flow consistent update. He doesn't have to tell us what invariant he cares about. He doesn't have to say, I want loop freedom, or I want no black holes, or I want an access control policy. Any property that both P1 and P2 obey, by definition, a per packet consistent update will obey for all packets. Because that packet will either experience the first policy or experience the second policy. So as an added bonus, the programmer doesn't have to tell us which invariant he cares about. You just have to tell us whether that is preserved by a per packet consistent update or not. Likewise, if the programmer wants to do any kind of verification that whatever invariant he cares about actually holds, he only has to test it on P1 and on P2, not on all combinations of possible update orderings that might happen in the network when P2 is installed. So whatever verification one wants to do to test that or check that the program is behaving correctly only has to be done on the old policy and the new policy, not on any of the intermediate states that could arise during the transition. So it makes the checking problem computationally a lot simpler to solve. So that's sort of the third piece. So essentially what we have in Frenetic is three different pieces. An SQL-like query abstraction that allows the programmer to specify what stream of events he needs to see from the network. A policy composition framework that allows him to write applications as a collection of modules that can be combined together in flexible ways. And finally, consistent update abstractions that allow the changes those modules make to the network to be done in a way that preserves consistency semantics, so the programmer doesn't have to worry about the intermediate states the network might go through along the way. So just to wrap up, there's actually quite a lot of related work here. This is a collaboration between programming languages and networking, and we borrow a lot of concepts from each of those two communities. So a lot of what's going on under the hood in our runtime system, I only sort of hinted at a high level how that works, it borrows a lot of ideas from work on functional reactive programming in the PL community. And also there's a lot of work in streaming databases that's quite relevant to the query language that we created. And there's also declarative languages like ndlog for specifying network protocols that relate to what we're talking about. The nice thing here is a lot of this is happening under the hood for us. The programmer working in our language is just using an extension to Python that embeds these composition operators and query languages. So systems programmers don't have to become sort of experts in Haskell or OCaml or other functional languages like that to be able to use Frenetic. But under the hood, we're taking advantage of a lot of those concepts to make our runtime system work correctly and efficiently. OpenFlow, there's been a lot of work on languages for access control and other kinds of policies on top of OpenFlow, and there's a proliferation of a lot of different controller platforms. Onyx is the one that Google developed with Nicira that they use on their backbone. Pox is an open source platform that's developed at Berkeley. Floodlight is developed by a Java-based controller developed by Big Switch, another startup. Nettle is developed by Paul Hudek's group at Yale, and FlowAdvisor developed at Stanford. And there are a bunch of different testing and debugging tools that people have built on top of OpenFlow. And of course, there's all the work on OpenFlow itself that plays a big role here too. So just to conclude, I think software-defined networking is a really exciting topic area. It's a way to lower the barrier to innovation inside the network and to allow innovation in a part of networking that's often been very difficult to innovate in, which is the actual management of the network itself. And also provides us a really interesting opportunity to rethink the way networks operate from the ground up. And yet, at the same time, have some chance of those ideas seeing the light of day, because we're seeing that really commercial switches support SDN. A number of deployments exist in SDN, particularly at Google and with Nicira's product. And we're starting to see the beginning in this work and in a number of the other projects I mentioned, the beginning of some of the higher level abstractions that will hopefully make it possible to write sophisticated applications that are efficient and reliable. And I just think for people interested in making networks more reliable and more efficient, there's a really great research opportunity to do work that has both practical importance and an ability to help put networking on a stronger foundation than it's been on before. And as I mentioned a number of times, it's a large joint project between Cornell. Nate Foster is the lead person at Cornell, and my colleague David Walker at Princeton. They're both experts in programming languages, and we're working with a number of great postdocs and grad students on Frenetic. If you go to freneticlang.org, we have the source code for the system I just described available online at frenetic.org, freneticlang.org. And also we have an overview paper that summarizes some of the main ideas I talked about in the presentation. I'd also be happy to take any questions.